L'Hopital's rule tells us how to take the limits of functions that are one of the 7 indeterminate forms. Like, for instance, you already know about 0 over 0, and an even sign infinity over infinity. So for instance, if we were taking the limit of x squared minus 9 over x minus 3 as x approaches 3. First rule of limits is fill in the number first. So if I fill in 3, I get 0 in the top and 0 in the bottom, which means we're going to keep looking. And so what we would have done back at the first of the year and the end of last year is we would have factored and canceled and then filled 3 into the leftover, and it gets closer and closer to 6. So there's actually a hole in the graph, a point of discontinuity at 3, 6, but the limit as x approaches 3 from the left and the right would be 6. This just gets closer and closer and closer to 3, 6, infinitely close, so the limit does exist. Quite often, almost always, the limit does exist in one of our 7 indeterminate forms. What L'Hopital's rule tells us, though, is this. Instead of factoring and canceling, or other algebraic techniques that we learned, or trig identities, different things like that, he found that you could take the derivative of the top and the derivative of the bottom. So if I take the limit as x approaches 3, if I get one of the 7 indeterminate forms, always check that first. Then you can take the derivative of the top, which is 2x, and the derivative of the bottom, which is 1, and then you can fill in 3. 2 times 3 is 6, and you get the limit. Now be careful, it is not the quotient rule. L'Hopital's rule is if you are taking the limit of f of x over g of x as x approaches a, and you get one of the 7 indeterminate forms, of which I'll list in just a minute, then you can also take the limit as x approaches a of the derivative of the top and the derivative of the bottom. The quick answer to this is why this works is local linearity. This tells the behavior of the graph close to a of f of x, and the derivative of g tells the behavior of the graph. It's obviously a much more in-depth proof of that, but it's not the quotient rule. So we're going to take the limit of the top and the limit of the bottom, and we're using L'Hopital's rule to try to find a limit. Right now we're not even talking about finding derivatives. We're talking about how to find the limit. Alright, so let's talk about what determinant forms are. Like 5 over 5 is 1. I can determine that. 5 over 0 is definitely undefined. I could determine that form. I can determine what is going on. 5 to the 0 is 1. Let's see, 0 over 6 is 0. These are all things that I can determine. The 7 indeterminate forms are things that we can't determine, like what's happening when we put 0 over 0. And we're talking in terms of a limit. So if we're talking in terms of a limit, as this gets closer to 0 and that gets closer to 0, unless they reach absolutely 0, those could be two different numbers, like 0.0000001 over, something even smaller, where we've called the limit 0, but it's not a 1-to-1 ratio, and so so it's one of our indeterminate forms. We cannot determine, and many times it's not what we think. Like, what would we even think happened with 0 over 0? Some people would say, well, a number over itself is 1. Some people would say if you divide by 0, you get 0. Some people would say if it's 0 on the bottom, it's undefined. So as you see, it doesn't fit any of the criteria as one of these weird indeterminate forms. Infinity over infinity is another one of the 7. Again, we would think, well, is that 1? But it's not a 1-to-1 ratio because different infinity is not a set number. And so when I've taken in the past a limit of a function as x approaches a number and it's gone off to infinity, and then I take the limit of another function. They may even approach infinity at different speeds. One infinity you might think might be a trillion, the next one might be 1,000,000,005. So it's not a 1-to-1 ratio. It's one of the other indeterminate forms. Here is all 7 indeterminate forms. If you get any of these, use L'Hopital's rule. Infinity minus infinity, 1 to the infinity, 0 to the 0, infinity to the 0, and 0 times infinity. Do I have 7? 1, 2, 3, 4, 5, 6, 7. This is one of the indeterminate forms because when you subtract 2 infinities, like I said, they're not set numbers. And so you won't get what you thought you would. You cannot determine it. You originally may think that infinity minus infinity would be 0, but it's not because it could be 2 different numbers. 1 to the infinity is very interesting. If we look at this limit, for instance, is a classic case of it. 1 plus 1 over x to the x power as x approaches infinity. If we reason it out in our head, as this gets closer to infinity, this gets smaller and smaller, and so this number inside here gets closer and closer to 1 to the x power, which is infinity. But if you type this into your calculator and you let x grow and grow and grow, you'll see that this number hovers toward 2.718. In fact, the answer to this is surprisingly e. This particular one. 1 to the infinity doesn't always equal e, but it's a classic case of it. And we'll do this one later using L'Hopital's rule to prove that it's e. But 1 to the infinity, if you're talking about a limit, which is all we're talking about right now, if you're talking about a limit, you might not have exactly 1. If you have a little bit less or a little bit more as it grows to infinity, it can accumulate to some interesting things. 0 to the 0, again, it cannot be determined, much like 0 over 0. Like, for instance, if you have 3 to the, let's say, 8th over 3 to the 8th, that's 3 to the 0, which is definitely 1. But if you have 0 to the 8th over 0 to the 8th, you get 0 to the 0, which is the same thing as 0 over 0, which is one of our 7 indeterminate forms. Infinity to the 0 power would give us like infinity over infinity. If we raise it to a power, let's say even 1, that would be infinity over 0. So it goes back to this one. And this one. The screen's gotten really messy, so let me erase some. 0 times infinity is also one of the 7 indeterminate forms. And so what I'm doing is showing how all of the indeterminate forms are really related back to 0 over 0 and infinity over infinity, which you actually have to get your function to be in that order or that form in order to use L'Hopital's rule, because it's the derivative of the top over the derivative of the bottom. So let's see, what was that at? 0 times infinity. Infinity is quite often defined as a number over 0 when you're talking about limits. Okay, so if you're talking about limits, like if you say 5 over a number, let me look at this one. The limit of 1 over x as x approaches 0 from the right. As this number gets smaller and smaller, the number gets bigger and bigger and goes off to infinity like this as I approach 0 from the right. And so if I'm defining infinity as something like a number over 0, then I have 0 times a number over 0, which you see gives me 0 over 0, so I'm back to this indeterminate form. It's really strange to try to talk about limits with something that's practically nothing and something that's practically infinity. Sure, if you had 0 times 5, you'd go on and call it, but what about 0 times infinity leads us to one of these 7 indeterminate forms. So let me list them again. The 7 indeterminate forms are 0 over 0, infinity over infinity, infinity minus infinity. I'm really bad at writing infinity on my iPad. 0 to the 0 power, 0 times infinity, and infinity to the 0 power. I don't think I have 7. 1, 2, 3, 4, 5, 6. I'm missing 1. 0 to the 0. Oh, 1 to the infinity. They're all really strange. Like, we think we could determine some of these, but they're indeterminate forms because they can all be written as one of these two forms. And so let's look at 1 to the infinity and see how we'll attack this. Let's say if I want to take, or just like a proof of it, like if I have y is 1 to the infinity. In order to get to that infinity, I'm going to take the logarithm of both sides, which is actually going to be one of our skills. And so I get ln y. I bring down infinity, and I have infinity times ln 1. So I have ln y is infinity times ln 1 is 0. So as you see, it led me to one of the other 7 indeterminate forms. Infinity is often defined as a number over 0. And so that would be 7 over 0 times 0, which gives you 0 over 0. You're just in the circle of indeterminate forms. So how will you use this? Suppose you have the limit of x ln x as x approaches 0. All right, first of all, what does that give me? When I fill in 0, first rule of limits is fill in the number first. When I fill in 0, I get 0 times ln 0. ln 0 is going off to negative infinity, which if you factor out your negative, it sort of doesn't matter here. You're getting 0 times infinity. You have one of the 7 indeterminate forms, and that means you've got to keep on going and look for the limit, in which case you'd like to use L'Hopital's rule because it gets you out of doing a lot of algebra. But the L'Hopital's rule tells you that once you get one of the 7 indeterminate forms, take the derivative of the top and the derivative of the bottom. If it's already a quotient, that's really easy. If it's not already a quotient, you have to manipulate it until it is. Like, for instance, I can call this ln x and 1 over x. Now let's see what I have. So instead of multiplying by x, I divided by the reciprocal. So this statement still is x ln x. I'm just engineering it. Now when you fill in 0, you get negative infinity and 1 over a very small number, when you're talking about limits, goes off to infinity. So if you can get it to 0 over 0 or infinity over infinity, you can move on with L'Hopital's rule, because now I have a fraction. So now I can use L'Hopital's rule, take the limit as x approaches 0. The derivative of ln x is 1 over x. The derivative of 1 over x is negative 1x to the negative 2. And let's see, I think I've got to go to another slide, or let me erase some of this so I can continue writing. Okay, sorry about that. All right, so this is the limit as x approaches 0 of 1 over x times, or over, negative 1 over x squared. So you have the limit as x approaches 0. If I multiply by the reciprocal, I get negative x squared over x. So I have the limit as x approaches 0 of negative x. And so I get 0 for my limit. So on other problems, look in homework and very typically on the AP exam, you have things that are already in quotient form. Here as x approaches 0, you get 0 over 0. And so now, I mean, you could have used an identity to probably get out of this, but we can use L'Hopital's rule. The derivative of the top is cosine. The derivative of bottom is secant squared. And now when you fill in 0, cosine of 0 is 1, and the secant of 0 is also 1. And you just get 1 for your limit. One other thing, suppose that you had this, the limit of x cubed plus 3x squared over 4x squared plus 2 as x approaches 0. Let's make this 4x cubed. All right. Now this is not, I could also do as x approaches infinity, and we would look at our highest powers, but I'm going to leave it at, here's an interesting one. I didn't mean for this to happen. If you fill in 0, you get 0 over 2. So the limit of that would be done. You would get 0. It is determined. Let me put this in here, and now we're getting 0 over 0, one of our 7 indeterminate forms. So I'll use L'Hopital's rule. Because this might not be too hard to factor, but maybe we couldn't even do it with algebra. The derivative of the top is 3x squared plus 6x. The derivative of the bottom is 12x squared plus 2. When you fill in 0, you get 0 over 2. Oh, hang on. Didn't want that to happen. Let me change it. One more thing about it. To give you this illustration, let's make this 2x squared. Okay, so now we've got 0 over 0. I'm using L'Hopital's rule. The derivative of the top is 3x squared plus 6x. The derivative of the bottom is 12x squared plus 4x. And the reason I wanted to plow ahead with this is now if you fill in 0, you still get 0 over 0. As long as you're still getting 0 over 0, you can continue to use L'Hopital's rule. You can just go until you do not get one of the indeterminate forms. So here I get 6x plus 6, and here I get 24x plus 4. And now when I fill in 0, I get 6 over 4. And so the limit of this function as x approaches 0 is 3/2.